Okay. All right, guys. I'm going to turn this audio up a little bit.
Like close the door, or would you?
Yeah, why don't you close the door? I'll leave it open for now until it gets loud. Okay. Okay, everybody. So it's my pleasure. This is our last actual class, and it actually is kind of working out well. That's Federico Vici up there. Federico Vici. I keep calling you Vicini. Federico Vici. He's a researcher who does a lot of work with machine learning and artificial intelligence stuff. He's also a good friend of Nicola's, so yeah. And he did a lot of work with a guy that I used to know pretty well, named Atao Tanaka. And Atao, yeah, you've seen his performances, haven't you, Federico? I haven't seen him for like 15 years.
But yeah, like we perform together, and we're like frequently in touch. We work together, yeah.
Well, the thing that was great about his performance, he did a lot of work with looking at electromyograph signals. Mm-hmm. So he puts sensors. But the thing is, he's this Japanese guy who is really well built. And his performances, he'd get up on stage and just go. And this cool sound would come out. Don't tell us how I said that. Anyhow, so Federico just got his PhD not too long ago from University of Plymouth over in the UK. And since then, he's had some really interesting postdoc positions. Yeah, he was at Goldsmiths, where I assume you probably knew Rebecca Febrink.
Yeah, she was there. Like now she's at UAL, but while I was there, she was there. Yeah.
Cool. He was at the Universität Hamburg doing some work there. I had to write some of these down. And he was at the University of Oslo, which there's a lot of computer music going on there. They've got a really great facility doing really cool stuff. And he was also at a place I didn't know about, Luleå, Sweden, which sounds like it's pretty interesting. And yeah. Since then, he's been back in Berlin, where he's working at the Universität of Kunst in Berlin. And actually, he's just done a lot of work for a lot of people. And like I said, the thing that makes him interesting for us is that a lot of his work is focused on gesture recognition. And that's the one thing we haven't really been able to do with the other packages very easily. We looked at the Wekinator, ML Star, and of course, Flucona. But I'm really interested in hearing what he has to say. So welcome, Federico, and take it away. Yay.
So thank you so much for the introduction. So I'll do a little audio test to make sure that you hear when I'll share my presentation. All right.
Yeah, that's a good idea.
Mm-hmm.
Perfect. All right. Sounds wonderful.
Yeah. Awesome. All right. So I guess like Brad did already the introduction, so thank you for the very nice introduction. I have prepared a presentation for you today that like I'm trying to sort of trace a trajectory that goes in and out research and in and out artistic practice. I'm trying to kind of explain what the research is about and try to give you an example of the way I've applied these ideas into artistic practice. So perhaps like the trajectory will be sort of a bit of a zigzag, like in and out academia and from research to artistic practice. But I hope it sort of is like a good way of putting things into perspective, so to speak. So as Brad said, I got my PhD at the University of Plymouth and the Interdisciplinary Center for Computer Music Research. And there I started studying more closely gesture and sound. So for me, that is like the point of departure for a whole lot of my research and my practice. And Particularly, I'm interested very much in embodiment in an electronic music, and I'm going to play a short excerpt. So this person here, many of you may know him, is Michael Weisfis, and he was the director of STIME, a very important and unfortunately now defunct laboratory for electronic music in Amsterdam. And years ago, way before I got into academia, I attended a workshop at STIME, and like, for me, it was very fascinating to see how they were approaching interacting with synthesis, with electronic music, and with synthesized sound. And this, for me, has a lot to do not just with electronic music, but like how approaching instruments conditions our way of experiencing music, how like we connect gesture and sound and the act of producing sound to like a very embodied performative activity. Okay, and this leads to like one of the core theory that I explored during my doctoral studies, that of embodied music cognition. So like gesture and corporeal imitation being fundamental constituents of human expression and also of musical expression, and the fact that there's like a repertoire of gestures linked with the resulting experience and sensations of music. So like there's a gesture action oriented ontology, using more like technical terms. And so this is like a model of embodied cognition. So rather than having the kind of typical disembodied model of cognition where you have, you know, perception that gets qualia into some person's mind, and that results in an action that is a reaction to what is perceived. Here, the model is, you know, the embodied mind being like a brain within a body that experience the world not just by passively receiving stimuli, but more like by acting onto the world. So like you perceive through action. So music is something we do, it's not something that we passively perceive. And so that's why, for me, gesture is so fundamental in the way like I'm understand and experience music. No? So since the course that you know, I'm happy to do the final session of is a lot about data and sonification. A whole lot of my research has to do with kind of transducing gesture into data. So like kind of see how like gesture can be captured and turned into data. And that, of course, can be done through technology, various kinds. Recent, less recent. Top left is a synthesist here in Berlin that performed with us on a telematic performance where we were like capturing his gestures through infrared motion capture while he was playing his modular synth, and that was affecting how the sound was spatialized into other locations that were connected via the internet, one in Stockholm and one in Oslo. And on the right of the slide are like various wearable devices those bracelets are the ones that actually Tao Tanaka uses for electromyogram. They're called the myo armbands. Then there are various inertial sensors, various other things that have been part of my practice in various ways. So like the next step into making sense of motion data is to extract what is known as motion descriptors. So like some meaningful quantities from raw data. So like to kind of make sense of the raw data that you get from motion capture or from wearable sensors, and try to obtain some useful quantities that perhaps are linked with certain expressive qualities of the gesture. And there's like a quite broad literature about computable expressive descriptors of human motion. There's a conference that is called MoCo, which stands for motion computing. There's lots of people that work with these concepts. And I myself, I work with these descriptors in my practice. So some examples of descriptors: contraction index. So it's like high when the body is contracted, low when it's expanded, and the quantity of motion, which is an aggregate descriptor of how much movement overall there is in a certain area of the body. And together with a friend of mine, Rodrigo Schramm, we looked into linking this idea of quantity of motion to the rhythmic subdivision in like a musical excerpt. And so technically speaking, the quantity of motion signal is passed through a filter, an array of filters that have like the resonant frequency synced with different rhythmic subdivisions. So you get the signal decomposed in various components that like resonate with the rhythm. So let's kind of see an example of this. So here,
Federico?
Yeah.
I got a quick question. So some of the descriptors are static, like the contraction index, but other descriptors encompass motion over time, correct?
Yeah, some are static, and some other are that are more like they're windowed in a way, so like they refer to a time window.
Okay.
And then there are like other things that are more like time-based, so like temporal modeling, for example, where you have like a gesture template and you use certain algorithms to kind of look at how faster or slower you are compared to that gesture template. And so that's known as temporal modeling. There are various techniques to do so, such as gesture following or gesture variation following, some of which are in MUBO, by the way, because they've done lots of research around those topics after CAM. But this is another thing. This has more to do with the idea of entrainment. So like synchronizing with rhythm through your body, a bit like this person does here. Oh wait, let me go back. There were two rhythms there. You saw like at the beginning the headbang and then the faster one. So there were like two different rhythmic subdivisions, no? And so like back when I was doing research on this in Plymouth, we tried to sort of have like an indicator of like which rhythm subdivisions the body movement resonates with. And we came up with this periodic quantity of motion, which looks like here you see like the blue plot is the resonance with a quarter note. And so in the first part, you see it's much higher than the resonance with the 8th note. That is when like the head banging sort of went like twice as fast. And that's because of the resonance with the filter bands that were had the same frequency as the corresponding tempo of the quarter note and the 8th note. And continuing with this, after like my PhD, I started working with a friend of mine there in the US, Luke Dahl, that is at University of Charlottesville now, on a Max library for extracting motion descriptors from raw motion capture data, like contraction index and velocity acceleration, bounding boxes and whatnot. And this is called MODOSC, which stands for Motion Descriptors OSC, because everything is bound to OSC addresses. And yeah, it all works. It all works in OSC using the ODOT library by CNMAT. So everything is calculated using expressions into these objects that calculate useful motion descriptors from motion capture data. And so we went from like gesture to sound, transducing sound into data, and then extracting useful descriptors. And here it comes the idea of interactive machine learning. So these are the first 2 steps: transducing movement into data, extracting motion features or descriptors. And then what happens next? You use machine learning models that are fed with motion descriptors and sound parameters to train a model that somehow maps these parameters to sound. And you do this through what is known as supervised learning, meaning that you demonstrate to the computer how you would like the gesture to correspond to the sound, record some data, train a model using artificial neural networks or other approaches, and then play the resulting trained model. And there's since we were speaking about Rebecca Fibring, there's a nice chapter that she wrote together with Baptiste Caramieux about the machine learning algorithm as a creative musical tool that is in the Oxford Handbook of Algorithmic Music. And it's I really like that book chapter because they look very like they're both very proficient computer scientists, both Baptiste and Rebecca. But they look at it more from also, what are the affordances of this machine learning models for like, a person that like an artist or like a musician, like more, they look at them more as instruments rather than computer science concepts, okay? And so I've made a like Max package that works a little bit with this concept. It's called Gimlet. I'm going to show you a little bit about it.
Okay, so in this video, I'll show you how to use Gimlet.
Instead of playing the tutorial, which is online, I'm going to give you a live demo. So there in that video, that was the learning and playing procedure that I was talking about using the accelerometer of an iPhone. But here I can show you the Max patches, and I have, in this case, like this is called the wave ring, and it's just a ring with like an inertial sensors that you can use to send data to MIDI or C or whatever you like. And so here you can see my cursor, right?
Yeah.
Yeah, cool. So here there's the data from the ring that I have in my right hand, and they're like 3 axes. I'm also going to zoom a little bit so you see it a bit better. Yeah. And this is actually an additional view of the same patch. It's like 3 tabs of the same patch that I open onto Windows to show them side by side. And so, like, what you can do with this is to use the scenes. This is just like a sampler that you can use to manipulate and filter sound. It's a kind of typical Mac sound, so to speak. So you can like you have 6 parameters here that also appear here in the machine learning module. So you can kind of make a sound. Let's turn on the DSP. Adjust the parameters so whatever you want. Say like kind of do a kind of a droney thing, and then what you can do is to like associate as some motion data to that sound. So here I just add 1 second delay to the recording, so I can press record and do something with my hands, like that, for example. Over here. And then I can like something like this. Data, like my hand like this. Finally, let's go here.
Hey, Federico.
Yeah.
You're tracking your ring, you say? How's that tracking accomplished? Is that a special ring or?
This one. Yeah, it's like it's called Genki Wave. It's kind of off-the-shelf motion sensor that is.
I would send it to you. It's
Okay.
a Bluetooth motion sensor that a lot of people are using these days.
Yeah.
Can we buy one?
Sure.
Yeah, it's like $200 or something, but I think it would be
Oh,
great.
$200? No.
I think it would be great for the CMC to have it.
Okay, let's alert Seth.
Yeah,
We
they're
usually we have money at the end of the year that we
Yeah.
have to burn
Yeah.
out, so we'll get some of these.
Yeah, job for sales, very good.
Great.
Sorry.
No problem. So yeah, or something like this. I don't know. And then you record more data in another posture. And then when you train your model, you have like a different posture that you have mapped to the corresponding parameter, and then you can move in between.
Oh yeah.
I see.
You could
And this is something that you can do also with the Wakinator. It's like they say, like it's basically an implementation of the interactive machine learning paradigm, where like you show things to the system, and then like you build the model starting from these like anchor points, and then move in between like the resulting parameter space that is created between like the gesture space and the sound space, rather than
is that also working with an MLP?
With an LP?
MLP?
Yeah, the multi-layer perception. You mean? Yeah, it's similar. The architecture of the network is, if you're referring to, it's an MLP actually. The architecture of the network is a bit, what is it called? Like non-conventional because you have like a mini network per feature in this situation rather than having a network that gets all the features. But at the end of the day, yeah, they're like several multi-layer perceptions.
Okay. Okay.
Or what is the input, the gesture space?
Did you hear that, Federico?
I heard it coming from afar, so I
Okay.
couldn't quite.
It says, what is the gesture space?
Yeah, what is the gesture space?
For gesture space, like in this case, we have 3 parameters here on the left, which corresponded to 3 axes of the 3 axes of this motion sensor. So for space, I mean more like in sort of like geometrical or mathematical space, meaning like the space defined by a set of parameters. So whether it's like Cartesian coordinates or rotational axis or however many parameters you have, then you sort of create a space. And then you have a parameter space on the sound side that can have however many parameters you wish. And what machine learning does is somehow to connect these 2 heterogeneous spaces, these 2 like different multi-dimensional spaces.
I wonder what's the difference between this one and a typical 3-axis accelerometer?
Between this one and a 3-axis
Accelerometer?
Yeah, they're very similar. They use a similar technology. So like an accelerometer usually has 2 or 3. Yeah, you said 3 axes. So in that case, definitely 3 axes of like through a 3-axis accelerometer, you can measure linear acceleration through the 3 axes, right? So in something like this, there is also like a gyroscope and a magnetometer that allows you to kind of measure the orientation in space rather than just like the acceleration on the 3 axis or like the rotational velocity. So this is technically, then there's like an algorithm that fuses the data from all the sensors to then also compensate drift and lots of other problems that you may have with this kind of sensors to then give you like this orientation on 3 axes that is then also static. Like an accelerometer, when you don't move, you get just almost 0. In this case, you always get some kind of rotation relative to your space.
That makes sense.
You could, by the way, if you remember, also do the same thing with an Apple Watch. With that software, the Holon IST, that also provides you the orientation. So it knows where it is in space.
Is it computing out from the accelerometer data then?
It's accelerometer and gyroscope, but it's also fusing
Oh,
the
it's got a
data. So
gyroscope in it.
you get an
Okay.
XY orientation and it knows where it is.
Can I ask one?
Sure. One more question?
Like, why do I need the neural network here? Because I think we definitely want to overfeed. Because you want to, like, one gesture mapping to one sound, another gesture mapping to another sound. Why don't we just map it? Like, if we wanted to sound that way, why do we need?
Because everything is tweaked.
Well, if you just like give a range of the tolerance of mistakes, I mean, you can't say like exact 1, but you can like, if it's in the range of 1 to 10, we make this sound, another.
Like just linear.
Yeah, it's kind of difficult to hear, but basically, like what you're saying here, why don't we manually map different ranges to different?
Yeah. Why do you need a neural network to do it?
Yeah, because that's a good question. So if you did it manually, like you would have to kind of find a way to map something that has a different dimensionality, in this case 3 against 6, and so you would have to find sort of like the functions that map a 3-dimensional space to a 6-dimensional space in the ranges you want, And it's kind of very impractical, especially if you're like workshopping ideas with other people and you sort of want to try ideas very quickly by just like putting sounds together, recording data that correspond to a gesture, and then like get the mapping very quickly. So if you were to do it manually, like there would be a very tedious work in sort of find the function that maps this 3-dimensional space to 6-dimensional space in the ranges you want. And so this is also the advantage of interactive machine learning, that it allows you to experiment a whole lot very quickly in a kind of workshop situation. Whereas if you were to like explicitly program everything by hand, it would be a bit of a tedious process that sometimes sort of kills the mood, so to speak. But you know.
yeah. Actually, that's what I was going to say too. It's a really elegant data reduction technique. You know, it's actually pretty smart about it too. So, yeah.
Can I just ask a kind of clarifying question, just to make sure I understand?
Can you hear okay, Federico?
Yeah, like maybe speak up a little bit.
Sure. So is the idea here that you have a bunch of prescribed audio clips or segments that then the user makes some gestures, and so each of these audio clips is like an anchor point, and then the user will make these gestures for each one of these different clips, and then you're just mapping, like you have prescribed audio, but then you're mapping these gestures that the user is making onto the sound that you already decided you're going to make.
Yeah, so like,
so it's like a fixed instrument in that like the instrument only produces the same sounds, but the way you produce those sounds changes based on how the person trains it.
Exactly. So this synthesizer here is like is actually like a sample manipulate, like it's just a sampler with a filter, and it provides an example of like mapping the sensor you have onto like a sound synthesizer that has 6 parameters. But here there could be an additive synthesizer, there could be a granular synthesizer with like 10 times as many parameters. Like the concept would still hold, as in you would go about kind of setting the parameters the way you want and pairing that set of parameters with a certain posture.
Right.
And so like it doesn't matter if there's a clip or not. In this case, there are like these 6 parameters, but you could have another synthesizer with a totally different set of parameters, and the thing would still work, even if there are like way more parameters. And actually, there's an example in the package here that I can just show you quickly. Let me see.
But then it's still up to the user, the person who's doing it, to decide what sounds they want, are like the target sounds that are these anchors.
Exactly. So like to define what that anchor point sounds like by selecting, by setting like the parameters in a certain way.
Right.
So like in the package here, there's like another parameter, like another example that uses a different model and
oh boy.
and 3 granular synthesizers. And so like it would work also with this because then you use the neural network to map like your 3-dimensional space onto like this multi-dimensional space of sound parameters. Yeah.
That would be hard to code by hand.
And so actually, I mean, unless there are more questions, I can then show you a little bit about how I sort of went, I sort of tried to extend this paradigm, you know, in some ways, or like also show you how I have applied it to some pieces, for example. Let's see. So yeah, this stuff is on GitHub. There are like a couple of tutorials, and like I'll send these links also to Brad. Then
right, I'll put them on the webpage then.
And so this concept of anchor point, I also try to apply to like music notation in a certain way for a piece. This is a piece like a rather old piece, but I'll play it. So here is well, 11 degrees of dependence, and the saxophonist is Catherine Williams, and the way it's notated. So first of all, she has some sensors on her arms, and those sensors are mapped to a physical model of a wind instruments that, like, you could hear in the back behind their saxophone, that follows their movement, and these movements are notated. Okay, and so like these symbols here are like represent the anchor points that the model was trained with, and they correspond to as many postures. So like the circle is sort of rest posture, like the kind of natural posture that she would start with when she starts playing, and then there's this like arrow here is like leaning on towards the left, and then there's the other arrow leaning to the right, and the triangle is like when she rises the bell of the saxophone and like also opens a little bit her arms. And so this is like the notes are the same. It's like the same phrase, the same passage, but the movement notation is different. So if we compare it, so this is the first one. And then back out here, and then right. It's like on this poster here, so like open as much as you can. And so this was like an attempt to translate, or not to translate, but to transport that concept of anchor points that you use in interactive machine learning into music notation, to like also you know, Catherine is like classically trained, so for her it's kind of a way of communicating ideas for me to her, rather than talk about, you know, artificial neural networks or multi-layer perceptrons. Like it was a way also of like sort of finding a common ground to like share ideas and workshop the piece together. And another example of using anchor points, this is a picture from the R1 reactor in Stockholm. Like it's a former nuclear reactor, 26 meters underground in the center of Stockholm, and that pit there is where the nuclear reactor used to be, because this was like a secret what's it called, research lab that was active during the Cold War, where like the Swedes used to do experiments with like nuclear energy and things. And now there's like an organ there on the, this is like a Burlitzer cinema organ that was like from the 20s, that was in a cinema in Stockholm. And a person bought it and brought it inside the this like former like nuclear reactor lab. And the funny thing is that the case, the housing of this organ actually has the same shape as the reactor. So like they did it very similarly. So it's kind of to as a way of, you know, connecting the organ with the nuclear reactors. It's kind of funny, but like, yeah, apart from that, yeah, that's the organ. And we use this idea of anchor points to like map the movement of a dancer, a choreographer, in this case, also Nandes Karin, to like different timbres made by the organ. So now she's in the pit and she's wearing one, like a ring exactly like the one I was wearing when I show you the demo, and she is playing with the organ. I'm going to play a short video to give you an idea. So in this case, like instead of that sampler there was a very complex patch that was interacting with all the stops of the organ that are like, I don't remember how many they were, and a few other parameters of the notes. So in that case, there were like way more parameters than 6, but what, like the mapping approach was the same. So like to set the organ in a certain way in terms of stops and ranges, etc., and map it to like a certain posture of the dancer. So like the concept of using anchor points and for interactive machine learning was used also here, like similarly to how I used it in the notated saxophone piece and also in the short demo before. And so this, yeah.
I have one question that is about the mapping. Is the list of mapping? I mean, does the functionality work in a way that the list of mappings is unlimited, or is there a limit to it? Because I mean, there is no theoretical limit to what it could be applied. So I'm just wondering about the interface.
Yeah, I don't know if there's like a hard limit in terms of like how big a variable can be, because there's like, but like you know, virtually unlimited.
Yeah.
It's just that if you, like, for example, add a whole lot of anchor points, like your model becomes very complex and it's kind of, you know, it could be successful. Like one can try to add a whole lot of anchor points, but then things become a little chaotic in a way, because it's very difficult to like, I don't know, maybe it is even like, in my experience, it becomes a bit chaotic, but I don't want you to think that is wrong and you shouldn't try doing it, you know, like it could lead to some interesting, perhaps like unexpected results, but usually it gets very complicated very soon if you add a whole lot of anchor points.
Yeah, it seems like if the anchor points were too close to each other, that's where you're going to get some of the problems, I would imagine, right?
Yeah, it depends how you set your parameters. So like, for example, if in the gesture space, you're very close, and in the sound space, and you're like, your parameters are hugely different, then you would obtain, which may also be what you want. You may obtain like huge changes in sound with very small changes in movement, which is perhaps something wanted. It depends on what you want to get. Mm.
I don't think,
And
I don't think the model can converge like that. I mean, if you have like small difference in the input and huge difference in the supervised output, there's gonna be a convergence problem.
I couldn't hear that because there was something on the microphone.
Oh, sorry. I was trying to move it around to make it
I was
better.
just asking about the convergence of the neural networks if we are under that kind of circumstances you were talking about.
Yeah, well, in this case, yeah, it's a bit difficult. It's like this, you usually tend always overfit around the anchor points. So it'll work somewhere. Yeah, it'll give you some. Yeah. Yeah, usually because you're not trying to model something like as you would, for example, like if you have like ground truth, right? You sort of want to try to kind of have your model resilient to like kind of outliers and things like that. But in this case, like there is no ground truth. Like you decide the ground truth by providing the examples, and so yeah.
Got it. Thank you.
No problem. Yeah, so like you have you know, the more the parameters, the more the like different sounds that you can explore, right? Like also mappings can be a whole lot. We just say like, oh, okay, I can add however many anchor points I want to try to kind of explore different relationships between gesture and sound. And so this next thing I'm going to show you is like kind of, it's called assisted interactive machine learning, and is like an interaction design method that is based on deep reinforcement learning, that is developed for the purpose of exploring the many possible mappings. Okay, so there are so many mappings that you could explore, but sometimes it's also difficult to come up with these mappings explicitly. Like, okay, I set these parameters in this way and I associate them with these gestures. Like, what if I could program like an artificial agent to kind of show me mappings, and I sort of decide which ones I like and which ones I like less, and then let this artificial agent come up with new mappings following the feedback I give it. Okay, and this is the overall like rationale behind this idea, you know, like to kind of create some sort of creative partnership with like an algorithm that suggests mappings that I can try and without like explicitly programming them myself, and then I can save the ones I like and get some new ones, and then set aside the one I like for performing with them. So yeah. Experimentation, there are many possible mappings that you can play with. So like, what if I could collaborate with an AI to explore mapping I wouldn't normally think of? Okay. So this is a way of supporting the exploration of complex spaces such as sound synthesis with lots of parameters. You know, perhaps there are like sounds in your synthesis model that you wouldn't normally get to if you were to program the parameters explicitly yourself. And this perhaps is also useful to like kind of, you know, get some surprising results and break some creative deadlocks, trying to get perhaps sounds you wouldn't normally think of. And it's also a way of learning, right? Because you explore a machine, in this case a synthesizer, by sort of getting some some ways this machine could work, and then you learn more about possibilities, right? And And also like in the broader like discourse of demystifying AI and ML is like it's something also Rebecca Fielding talks often about like actively building something in order to demystifying what AI and ML do. And so this also connects to a whole lot of research that has been done in computer music since, I don't know, several decades ago. There's a whole lot of stuff done with like, in this case, genetic algorithms. This is a system done by Palle Dahlstedt back in 2001. And so he was exploring the huge parameter space of, in this case, I think it was a Nord modular synthesizer. Using genetic algorithms, so it would get sounds and then like mate the different sounds that he liked to create a new generation of sounds. So would use like genetic algorithms to generate sound presets through like mating and breeding, etc. And this one instead is another example of a that is like a touch, like a tablet connected to a Raspberry Pi that talks to like a desktop version of a Yamaha DX7 that is, you know, has like 100+ parameters. And so that uses genetic algorithms to come up with the DX7 sounds. And that was something done for Affix Twin by a collective in Cornwall. And so same thing, but with hardware this time different. So Raspberry Pi and DX7, and there are like lots of other examples in this paper by Yi King and others. It's called Automatic Programming of PST Sound Synthesizer using Deep Networks and Other Techniques. And so here instead, I adopted like a different approach. So reinforcement learning is one of like the sort of fundamental machine learning approaches together with supervised learning and unsupervised learning. So it works. This is like an image that I got actually from the Wikipedia article about reinforcement learning, and it's like you have basically like your algorithm here is like an agent in reinforcement learning terms, meaning that it's an entity that does something into an environment. Okay, so the agent does an action into your environment, and you as the interpreter, like in this case there's a human interpreter, but it's not necessarily human. There could be another algorithm that sort of assess what the agent is doing, but that's a different chapter. So you as the interpreter look at what the agent has done in the environment and give some feedback to the agent in the form of a reward if you think the action is good, or like punishment, so to speak, if you didn't like what the action was like. And so reinforcement learning in recent years, like reinforcement learning algorithms have become very popular for like solving games. Like there was that AlphaGo by Google that was training on lots of games of Go, and with games is very easy to, I mean, it's a perfect use case for reinforcement learning algorithms, because you clearly know when an action results in something that can be considered like a good move or like a bad one, like an advantage. And so like the algorithm gets like positive reward, and it sort of tries to adjust its parameters in order to like recognize when that situation happens again and to do the right move at the right time. And so like this idea was also applied to sound design. And so there's this nice study that actually also came out of Kai. There's a journal, it's called Transaction on computer-human interaction. And they apply this idea to like programming BSTs. So there's an agent that sets like the parameters of your BST in a certain way, and then you listen to the sound that comes out, and you give feedback to the agent, and the agent tries to like set your BSTs in a way that you like, depending on what kind of feedback you give to them. Okay. And so my idea was actually to like apply this concept to the interactive machine learning paradigm. So like this is how we did things before, right? So you have motion, you extract features, then you train a machine learning model from examples that basically pair synthesis parameters to motion data. Okay, so it's that idea of supervised learning. You show things to the computer and you record data, and then like you train the model using whether it's like anchor points or like temporal modeling, etc. So here instead, like you have the agent that gives the examples to the computer. So like the agent comes up with some training data, and then you tell the agent whether you liked the resulting mapping or not. And so that this is how we came up with the idea of assisted interactive machine learning. This was actually a collaboration with Atao Tanaka and also another person at Goldsmith, Michael Spesinski. And so this is how like the whole workflow works. You basically give feedback to the agent. The agent comes up with some training data. It trains a model, you play with it, and then you decide whether it was something that you like or not, and then you get another one, and so on and so forth. So this repeats, and then you just save the ones that you want to keep. And so in terms of synthesis, this time we use another approach compared to the ones I've showed you earlier, which you may have heard about already, especially since Pierre Tremblay was there a few weeks ago. I think he uses it a lot, corpus-based concatenative synthesis.
Yeah.
And so I guess you already know a little bit about it. Like you have this big database of sounds that are then like cut in very small fragments, and these fragments are ordered in various ways or explored in various ways. Like on the left here, I think they're ordered in like a sort of three-dimensional space using features. Yeah, like there's fundamental frequency, spectrum centroid, and the color is like the loudness. In our case, we used this interesting algorithm that is called self-organizing maps. And so it is interesting because it avoids having like big areas of nothing in your corpus. You see here, there's like a big empty space, and self-organizing maps is an algorithm that tries to like spread your data in a certain way, so that you kind of, especially for corpus-based concatenative synthesis, you don't end up having some like holes in your corpus. And
one question, is that the self-organizing maps which people find in the ML star externals, or is that another one?
This one is another one that this friend of mine, Jonas Margraf, did for his thesis at TU in Berlin. Mm-hmm. He wrote it from scratch. I mean, the algorithm is probably the same that you find in ML star because it's a published algorithm, but he wrote it in JavaScript. And yeah.
They're all based on the Cohonen feature maps, right?
Yeah. Mm. And so here, for example, like to show you what it sounds like, so this is like a corpus, a short one actually.
close to you in your heart, brand new.
A bit long. Maybe I can just give to give you an idea. Like these are all the sounds that are in the corpus, and then when you apply corpus-based concatenative synthesis to it and map it to motion data, you can like articulate the sounds with that. So yeah, and also here.
Yeah, check that out. They're getting all that information from the MyGraph. You know, I think that's just magic. That's really amazing.
Do you have one of those at the CMC? Because they're not being produced anymore. It's a shame.
Well, Tanaka did it, right? I mean, he.
I don't. Did Atao develop this one?
No, those ones were developed by, these ones were developed by like a Canadian company that was then, like they stopped doing this, I think 2018 or 19, and then they started doing like another thing, and then they got bought by Google.
Is the device picking up Moscow signals?
Yes.
Yeah, exactly. But it's so the cool thing about this is that it's I think 8 channel, right? 8 channels of data at the same time. There's now another company that produces like a Myo band for the Apple Watch. So you can like exchange the wristband and put this and do this. I didn't get a chance to try it yet. I don't know if you ever had a chance to try that one.
No, not unfortunately. No, I'd be interested in doing that. Yeah. Yeah, so, but, you know, it's an interesting device. It still works if you can find one. So, but yeah, in this case, for example, like you could hear some of the timbres from the corpus, but like there's a whole lot of grains of that corpus that with this particular mapping are not reached. And so that's why it's interesting, in my opinion, to use artificial agents to explore complex mappings, especially with corpus-based concatenative synthesis, because there could be lots of sounds that you know, are somewhere in the sound space and you're not actually finding them. But on the other hand, having a mapping that like virtually allows you to touch every single sound might end up being kind of a bit overwhelming in a way, like that it makes it difficult to articulate you know, sounds like I was doing here that have like a certain, you know, characteristics, because like you would touch so many different times at the same time that it would be very difficult to do something that is not too complex. So it's to me it's a good use case for this kind of exploratory algorithms because of the complexity of the sounds that you can make. And so to like delve a little bit into like artistic idea around this concept of assisted interactive machine learning, I have you know, come up with this way of exploring personal memories that are turned into data. So there's, you know, like you have lots of memories in your phone, right? And sometimes some phones or even some social media, they remind you of some memory that like you experienced like a year ago, 2 years ago, because they scan your photos, they look at the features of these photos. They put together sometimes even a short slideshow, and they come up like with a notification on your phone that says you have a new memory, and then you look at it, and then like there's this sort of ridiculous slideshow of your vacation or whatever. And but that sort of made me think a little bit about, you know, how data is then used to sort of prompt memories in a way that is automated. And, you know, like memories are also a big part of like our identity, right? What we think we are. And so the fact that this is automated by an algorithm, to me was like a kind of interesting thing to explore. And so like for this project, I put together a whole lot of the audio messages and short videos that I recorded while traveling, and audio messages I received from lots of people like on various messaging apps, and built this like corpus of personal memories, of personal sonic memories, right? That I then explore using artificial agents and motion sensors. And so like I applied the assisted interactive machine learning to like explore this archive of sounds that I collected in the like along 2 years or something like that. And
yeah, I'm gonna go.
No.
It's gone now. It's gone now.
Yes.
And so there I also, for the visuals, I was also using like the photos that were on the phone that were then like ordered using metadata and various other things. And so it was kind of an interesting experience, like, you know, lots of very short fragments of sounds, like had some kind of, they sort of triggered some memory just to me, probably, and no one else. And it was interesting sometimes when like the mapping would juxtapose things that happened, I don't know, like a week before, and things that happened like 2 years before. And that would create like, you know, a way for me to like see those things from a perspective that I wouldn't normally like, I'd look at. And so this like led to like this project that is called ACAXA, that is like electronic music alter ego that I have on Bandcamp. That
Oh, I forgot to mention that in your introduction. Sorry about that.
yeah, that's all right, no problem. And so like last year I released this this record that is made, like one track is made using this concept of building an archive, a corpus of sonic memories and exploring them with algorithms. And then there are, of course, like other electronic musical instruments in the mix. And then like I was also playing a little bit with various media, like I put like the data in like an SD card and like sold it as some sort of, you know, like container of, you know, my own personal data, my own personal memory. And I also minted one of the memories as an NFT, since, you know, in 2021, like just anyone minted NFTs on the blockchain. So I just did that. And so yeah, like if you want to check it out, it's on Bandcamp there. And actually, if you like it, just send me an email. I'll send you like a download code. It's like a perk of just for you. Yeah. So other ideas around exploring corpora. This is something that I've done in Sweden at the Luleå University of Technology, and actually the music school is in Piteå, which is still up north in Sweden, but like several kilometers away. And there's this big pipe organ in the concert hall. And during lockdown, like on the top right, there is Stefan Osterho, who was my boss at the time. He's a guitar player and academic, and he was in Stockholm in his apartment, and I was in Berlin in my apartment, and we played with the organ that was in Piteå in northern Sweden, which received data from both me and like his guitar. And in this case, we recorded a corpus of recordings of like an instrument called the Aeolian guitar that we played, both him and myself, in an island near Piteå. So like an Aeolian guitar has very long sticks that are like played by the wind. And they make this kind of drony sound when the wind hits them. So we recorded like a lot of different lengths and wind intensity. It's actually very frustrating when there isn't much wind, because you're like there pulling strings and nothing happens. But then when you find, you know, the right amount of wind, and like it's actually like a very cool instrument to play. And so we recorded a whole lot of that and created a corpus to kind of interact with both the corpus and the organ. And so we had, in this case, sort of, let's call them four modules in our performance: the electric guitar that I was playing, the Aeolian guitar corpus, the organ, and the acoustic guitar that Stefan was playing. We started connecting them in various ways, using various techniques to create different interactions. And so, for example, here, I wasn't really playing the electric guitar. I was more like activating the corpus of Aeolian guitars that you could hear like in the background, those like sibilant stings. So we're using like spectral analysis and corpus-based concatenative synthesis to like getting sounds out of the corpus, while Stefan was like playing like Evo on the acoustic guitar. And sometimes instead we would, you know, rearrange things differently instead to have like just interaction with the organs. And so now like my guitar. Sat on the guitar, like the organ responded with the same frequencies, and so like we then explore different ways of using spectral analysis to get stuff out of the organ. And so then, like with the quartet, the picture you saw in the reactor before, like that was an early performance just as a duo, Stefan and I, and then we started that quartet where I also use assisted interactive machine learning to create rhythmic structures for the other three to play along with, and also to create like different timbre and to interact with the organ using artificial agents to like create a set of stops I wouldn't normally try to explore by myself. And so we did. By the way, like this time we had two organs in the network. One was the one in the reactor, and the other one was connected via network, and it's at the Orkel Park in Amsterdam, and we connected them all together into the same room, even though they were very. Yeah.
Cool. That was really.
Thanks. And yeah, this is called the TCP/IP quartet, by the way. And this was at 9 last year. So yeah.
Federico, I
Yeah.
have a tangent question just for my own personal interest. What communication system did you use to connect the remote spots from each other to each other?
Like audio, you mean?
Yes.
So this one time, I think we used Sonobus.
Okay.
Oh, yeah.
Okay. Right.
But before we used Jacktrip as well, and like we tried 3-4 different ones. Like for another performance, we used Jacktrip, and actually, like the latency and the quality was a bit better, but it was a bit of pain to configure.
Okay.
Yep.
Yeah. Sorry, I was just interested. Yeah. See when you had a
Oh no, I was just asking why there's no delay, but he was talking already.
Ah, right. Yeah.
I mean, did you send MIDI data between the organs, or how did you control the organs over the network?
It was so like the one here in the picture receives MIDI.
Mm-hmm.
The one in Amsterdam instead has his own system based on OSC that is called Sinua. It is actually very cool. I wish we had more time to explore it because you can control the air pressure per pipe.
Oh wow!
And so yeah, you can do really cool things.
Yeah.
Yeah.
Nice. And then which how to say? How did you make the network connection between those?
Yeah, that's
So I'm asking because so I did like network connections between OS X systems, but that can sometimes just be terrible in terms of firewalls. And then I found this other sort of hack that was developed by a person from CalArts, which very elegantly hacks around firewalls, but it's totally not public. And I'm just wondering if there's any smart public solutions out.
So like in this case, I mean, the for the MIDI to the organ there, obviously we were in the same room, so there was
easy.
a cable, but like
Okay.
the one in Amsterdam, we had one of them that so we used like a VPN, and we had an interface written in Super Collider by a person working at the Orgel Park. And like his name is Wouters Nue, and he wrote this really nice Super Collider patch that is actually probably also on GitHub. I can send it to you if you remind me.
Yeah,
but,
absolutely.
Yeah, it's sort of like a client-server structure that uses a VPN to like dispatch OSC messages to multiple clients.
Oh yeah, that's nice. That's very cool.
Yeah, I think that's how Miller Puckett's Quacktrip thing works too. He has a central server that facilitates the connections, and that's how you get around the
But he
firewall.
uses Jacktrip.
Quacktrip is built on Jacktrip.
Exactly. Yeah.
Yeah.
It's a superset, I think.
Yeah. Yeah. I mean, the nice thing is now that with Jacktrip since 1.5, the version 1.5, firewalls are not so much of a problem anymore. It used to be horrible, but now it's.
That's good. Yeah.
You know, one thing I really did like about this was the swell chamber, the lights that you had back there. That was really great.
And yeah, there are a few references for some of the things that I mentioned here. One is like a book chapter that came out in the Handbook of Artificial Intelligence for Music that Atawa and myself wrote. It's all about interactive machine learning and musical gesture. And the other one, there's like a conference paper where like we write more about the idea of assisted interactive machine learning that is from 2020. And yeah, there are like these are like the two main ones related to this presentation, I suppose. But in general, to kind of like reflect a little bit and then perhaps open up for discussion. Like here, I try to sort of trace a trajectory between research and artistic practice, like back and forth, to see how, like the concepts are like, explore and define and research and then applied into like different artistic constellations, so to speak. And in my experience, this idea of like using artificial agent is something creatively useful, that is like kind of able to surprise and help breaking creative deadlocks, and like also especially for the Concatenative project to kind of come up with ways of using a very big like sample libraries of personal memories that could be like like hours long. Was like a very interesting way for me to like use those into an electronic music track. And so like despite the various like dystopic scenarios, like using these things to me is like not a way of substituting people's creativity. It's like helpful and inspiring, but it's not really like, it's not that we let the algorithm do everything and we just like sit on the sofa eating popcorns.
That's my utopia.
Yeah. Good point. And but yeah, that's a nice way of seeing things, actually. But also another thing that can be seen in basically all the examples I've shown you is that I always try to kind of create an interplay with established practices, whether this is, like conventional music notation or like traditional musical instruments, or like sort of more established electronic musical instruments, etc. Like I always try to kind of play with the ecosystem in a way, because I find it interesting, not because it's necessarily the right thing to do, but it's like kind of an interesting way for me to engage with like established practices and see where like you can go with combining these two things. And yeah, and also like another big thing is like supporting exploration of complexity, like especially now that we can have easily access to like an unlimited number of ways of producing sounds that have themselves like a very high number of parameters. I find this like kind of very much perhaps like almost like pertinent with our condition of like having so much access to lots of things. So kind of supporting the exploration of complexity is for me something, because sometimes like having so many possibilities, it's almost, at least for me, like kind of it sort of blocks me, like okay, where to start, where to go, and yeah, and also like it's a way, I believe, for learning through doing, through like having an algorithm that like just messes things up for you, and then you kind of hear what they sound like, is sort of a way of understanding how the whole machine works. And so I also see it as like a tool for learning. And then once again, like demystifying AI by actively using, as also Rebecca and many others have said, Rebecca Fibring in the past, is also an important aspect to it. And yeah, this is it. Thank you so much. And of course, if you want to discuss about anything, if you have any questions, I'm happy to have a chat with you.
Yeah. Well, again, thank you. Yeah. That was a great presentation, Federico. I really appreciate it.
So much. Thank you for having me.
The very first point that you say in your reflections about using AI/ML, you found it to be kind of interesting. Did it meet your expectations? Did you have to like kind of try it many times before you got the mappings that you wanted, or was it a pretty fluid process for you?
It depends.
That's a great answer.
Yeah, like no, there have been indeed like I mean, there have been aha moments, and there have been like moments of just frustration, of course, and yeah, and like I try to, I don't know, kind of interpret the moments of frustrations in a useful way too sometimes, because then like you go and like, I don't know, play like a hardware synth with just a few knobs, and it's sort of like you look at it from a different side in a way, because like dealing sometimes with like these complex designs can be frustrating. Like it's a way of sort of, you know, going back and forth, different like ways of engaging with sound. And so there have been moments where like, you know, just like, okay, I had enough for now for the but no, on the other hand, like there have been like very rewarding moments where like you know, I would hear something like very unique, and then like for example, there was a time that I started making like lots of loops that I started like kind of mutating with that algorithms, and like in the space of you know, half an hour, I had so many rhythmical ideas that were kind of odd that I could play with, and that was really cool. Or also like the exploration of memories, particularly like at some point it was very like almost a bit too much, because it was very personal, and so that was yeah, a nice kind of mapping indeed. Yeah.
Yeah, I suddenly became aware I don't want to keep you too much longer because it's like 2 a.m. over there for you.
Yeah.
Yeah, and we really appreciate you taking the time for doing this. So yeah, maybe we better let you go to sleep or something. Yeah, I hope you don't have early morning tomorrow.
Yeah, I'll start around probably 10. I have like a Zoom call, like just like any other day.
Okay, you can do that in your bathroom, so good. Well, Federico, this has been really wonderful, and it's a great way to kind of end this class too, because we'll do projects next time, and I very much appreciate it. And
Thank you so much for inviting me.
And like I said, yeah, we owe you dinner over here, so you got to come to New York sometime, and we can hang out a little bit.
That'd be great. I look forward to that. Thank you so much.
Yeah, let's meet.
Thank you.
Let's meet in Berlin sometime soon. I'm back in 2 weeks.
Okay.
Oh, cool. Yeah, sure. Yeah, let's do that.
Yeah.
All right.
Okay.
Cool.
Bye.
Talk to you later. Bye.